why do we use linear approximations? And the simple answer is that lines are nice functions. And by nice functions, we mean that they're pretty simple to graph and they're pretty easy to take an x value and substitute into and get out a y value. So we like lines. And we want to use lines to approximate nonlinear differentiable functions. So the idea is I would have this curve, this nonlinear differentiable function, differentiable meaning I can take its derivative anywhere, so there are no sharp turns, there are no vertical tangents, and there are no places of discontinuity. So I can find a derivative at any point, and then I can find an equation of a tangent line at that point of tangency, which is the red line shown here. So this red point is the point of tangency, and this red line is the tangent line. And the point of this section is that we're going to be asked to approximate values on the curve, on the nonlinear curve. So maybe I might be interested in finding this point right here that's actually on the black curve. But curves, curved functions, nonlinear differentiable functions, might not quite be as easy to approximate without a calculator, let's say, or without a lot of work involved. So what we want to do instead is recognize that this red line, this tangent line that we are used to finding by now, the equation of this line is pretty close to this curve at the point of tangency and all points near the point of tangency. So in a little interval around this point of tangency, this red line is going to be a pretty close approximation to the actual curve. Now, once I get far away from this point of tangency, let's say down here, now I'm not really so close to the red line. So this is, this is a huge gap. This would be a huge error if I use the tangent line way over here. But if I choose this point, which is pretty close to the point of tangency, to approximate the curve, so in other words, I would be using this red point here on the line to approximate this black point here on the curve, that's pretty close. There's still a little bit of error, but the closer we get to the point of tangency, the less error that I'm going to have. So that's the idea. We're going to be substituting in different x values into the tangent line to approximate the values on the curve so that we can avoid potentially either a lot of work or maybe work that we couldn't even do without a calculator to approximate values on a curve. So what we want to do is we want to use lines to approximate function values, and those lines are tangent lines. So this formula is not new to us. This is the formula to find the equation of a tangent line through a point A f of A with slope f prime of A. Or this is really our y minus y1 equals mx minus x1. But of course, to find our m, we generally need to take a derivative and substitute in an x value to get a numerical slope. And then sometimes we may have to plug in our a value into our function to get out a point x1, y1. So again, this isn't a new formula. And what I've written here is just rewriting the formula so that it is a y equals function. So in other words, all I've done from here to here is add f of a to the other side. So you'll see this minus f of a, if I add it to the other side, and I've chose to write it in front, y equals f of a plus f prime of a times x minus a. Because now we're actually going to use this tangent line. So previously we just found an equation of the tangent line. Now we're going to need to use it. By use it, I mean we're going to substitute in a value for x and get out a value for y. So we often want to solve the equation for y now because we're interested in finding that y value, whereas previously we were just interested in finding the equation of the line. So that's why there was no need to put it in point or slope-intercept form last time. We just left it in point-slope form, but now there might be a just cause to simplify it first. So the main idea, the big picture here, is that near x equals a, so a would be the point of tangency, the tangent line and the function f of x, that would be the nonlinear differentiable function f of x, they are close to each other. So this statement here says that f of x, that would be the curve. In this case, that would be the black curve. The curve is approximately, this right here is the tangent line. The curve is approximately the tangent line near the point of tangency. So right here in this little interval around the point of tangency, this red line is pretty close to the curve. Once I move further away from the point of tangency, again down here or even way over here, now I'm not going to use this particular tangent line to approximate the function. I would instead pick a different point of tangency over here to draw a tangent line and use that tangent line to approximate the curve over here, of which is differentiable. So what we're going to be doing is finding equations of tangent lines, not new, but what is new is we're going to be using that tangent line to approximate a value on the curve. So by using it, I mean we're going to be substituting in values into the tangent line. All right, here we go with our first example. Write an equation of the tangent line to f of x equals x cubed at the coordinate point 2, 8, and then use the tangent line to approximate f of 1.9 and f of 2.01. So let's start with the basics. What we already know how to do is write the equation of the tangent line to a function at a particular point. So we have our x1, y1. Now we need to find our slope. To find the slope of a tangent line, remember that's just the derivative. So we can find the derivative using the power rule. We have 3x squared is our derivative. So this is the slope of the tangent line at different x values. We want specifically the slope of the tangent line at 2. So we're going to substitute 2 into our x. So we want f prime of 2. So 3 times 2 squared. And 2 squared is 4 times 3 is 12. So 12 is my slope, 12 is my m. So we can go ahead and substitute in our point, so y minus y1, and substitute in our slope, which was 12 times x minus x1. So my x1 value was 2. So here we have our equation of the tangent line. We've done this part before. Now we're being asked to go a step further and use the tangent line to approximate f of 1.9 and f of 2.01. So right now what I want to do is I'm going to go ahead and add the 8 to the other side of this line. So I have y equals 8 plus 12 times x minus 2. So this is a tangent line to the curve x cubed at the point 2, 8. Now let's get a little sketch going of what's happening. So x cubed, as we know, looks like this. And we substitute in 2 and get out the y value 8. So there's my point of tangency. And what we just did was we found an equation of the tangent line. So the tangent line looks something like this. So we found an equation of this line. Now here's what we're doing is we're saying that we want to find the exact value on the curve at 1.9, so that's a little less than 2, right? So 1.9, and then separately we want to find an approximation for the value at 2.01. So we are interested in finding actual points on the curve. So these green dots I'm drawing are supposed to be on the black curve, but instead we're going to find values on the red line, which hopefully you can tell are pretty close to the actual points that I'm interested in finding. Now I want to clarify that on this particular problem, we could actually do this without a calculator, just be a bit of work. So if I wanted not the approximation, the exact value for f of 1.9, I could just plug in 1.9. So that's 1.9 cubed, which is 1.9 times 1.9 times 1.9, and we can multiply decimals. So this isn't impossible to do without a calculator, but it would be quite a bit of work. Now on the other hand, here's our tangent line, which is approximately the function. So our tangent line is approximately the function near the point of tangency, near that x value 2. So notice I'm substituting in values near 2. So 1.9, 2.01. I wouldn't want to go ahead and substitute in something like -5. That's not going to be a very good approximation. -5 is way over here, and this tangent line is probably not going to be a very good approximation. So what I am going to do is just take 1.9 and substitute it into my tangent line equation. So what I'm doing is I'm finding y of 1.9. So y of 1.9 is 8 plus 12 times 1.9 minus 2. And now let's go ahead and do some simplifying. So I have 8 plus 12 times, this is going to be negative 1/10. So negative 1/10. And if I keep going, this is 8 minus 1.2 multiplying 12 times negative 1/10. And this gives me out 6.8. So in other words, we were interested in finding f of 1.9, but that was approximately y of 1.9. So y of 1.9 is the tangent line approximation to the actual value f of 1.9. And f of 1.9 is actually, if I plug that into my calculator, that's about 6.859. And then we just found that the value was 6.8, and that's not too far off. So now we're going to still use that same tangent line to approximate f of 2.01. So now I'm going to try y of 2.01, and this is just substituting in our values. So 8 plus 12 times 2.01 minus 2. So we get 8 plus 12 times, now we have 1/100th. So this is going to be 8 plus 0.12, which is just 8.12. And we can also think about how practical our result is, because if we're going to substitute in something slightly smaller than 1.9, we should probably get out something smaller than 8, which we did, right? We got out 6.8, and now we're plugging in something slightly bigger than 2.01, and we got out something slightly bigger than 8. So this should sort of make sense, and we see that there's not too much of a margin of error, and that's because we're pretty close to the point of tangency. So we chose values near the point of tangency. We don't want to get too far away from it. So to conclude this problem, we want to say that f of 1.9 was approximately 6.8, and f of 2.01 is approximately 8.12. Alright, let's move on to another example. We want to write an equation of the tangent line to f of x equals sine x at x equals pi, and then we're going to use the tangent line to approximate f of 3. So here we have our function sine x, and we have the x value of our coordinate point, we have pi. So our coordinate point is going to be pi, and if I substitute pi into the sine function, sine of pi is 0. So our coordinate point is pi comma 0. And our slope is going to be found by finding the derivative of f of x. So I need f prime of x, which we know is cosine x. And I'm going to need to substitute pi into cosine x. So I'm going to need to find cosine of pi. So cosine of pi is going to be -1. So pi is on the left side of the x-axis, right, where our cosine value is the x-coordinate, and that value is -1. So that's my slope m. So this is my slope, and this is my point. I can plug it into y minus y1 equals -1 x minus x1. So now, since there's a 0 on the left, this is really y equals negative x minus pi. So now we want to use this tangent line to approximate f of 3. So this one's actually different than the last one in the sense that I cannot just plug 3 into the sine function. I would need a calculator in order to solve that. But 3 is really close to pi, so we're going to be able to use this tangent line approximation and get a pretty close value. So here, if I substitute 3 into my tangent line, y of 3 is negative 3 minus pi. Now, there's still some margin of error that's going to happen even further if I attempt to figure out a decimal approximation to this answer, because pi, of course, is irrational, goes on forever. So if I wanted to get sort of a pretty good idea using a decimal of what y of 3 is, or ultimately what f of 3 is, I'm going to have to approximate pi. So in other words, I can keep going, and this would turn into an approximation because I'm about to use 3.14 for an approximation for pi. So negative 3 minus 3.14, I'll go to the thousandths place, so 3.141. And if I keep going with this, now this is negative, and if I subtract, I'm going to get negative 1.141, and the two negatives are going to cancel, and I'm going to get 0.141 as my approximation to y of 3. So it's almost like I'm now approximating an approximation, because ultimately this y of 3 was approximating f of 3. But I needed to approximate the value of pi if I were attempting to find a decimal approximation. So to get a real grasp on what type of number this is this a really small number? And we can see that it's pretty close to 0, which should sort of make sense to us, because when we substituted pi, which is pretty close to 3, into the sine function, we got out 0. So if we plug in 3, which is pretty close to pi, we should get out something that's pretty close to 0. And we've confirmed that by approximating the value of pi here. But ultimately, this portion here was not necessary. We could have just gone ahead and stopped and said that negative, the quantity 3 minus pi, is our approximation to f of 3. So this is a numerical answer. There was no need to approximate our numerical answer. And in fact, we really never put in an approximation for pi. We leave our answer in terms of pi. But for this example, I just wanted to go a little further to a decimal approximation so we can make sure that our answer made sense in the context of the problem, having to do with the sine function. All right, so for another example, here I'm being asked to use a linearization to approximate the square root of 4.1. So up here, I want to point out a linearization is just asking us to use a tangent line approximation. So a tangent line approximation is the same as a linearization, just turning it into sort of one word here. So we need to find a tangent line, which means we need a function to find the tangent line to at a particular value where we're going to draw that tangent line. So I'm trying to approximate the square root of 4.1. So we're going to need a function, and that function is going to be the square root of x. So I'm trying to approximate the function, the square root of x, at the x value 4.1. Well, a number that's really close to 4.1 that I can easily evaluate the square root of is 4. So I'm going to be in search of the tangent line to the square root of x at the value 4. So let's kind of think about what's happening on the graph for a second. If I draw the square root of x function, I know the exact output when I substitute 4 into the square root function. That output value is 2. What I really want to know is what happens when I plug 4.1 into the square root function. What is that actual value on the square root function? But without a calculator, right now I can't do this type of problem, the square root of 4.1. But lines, again, are nice functions. So what we can do, what we've been able to do, is find a tangent line right at the x value 4 to the curve. So if I were to draw that tangent line, it's going to look something like this purple line. And I'm going to be able to easily plug a number like 4.1 into that tangent line. So I'll be able to find the point, I'll be able to find the point right here on this purple line. And that's pretty close. That purple dot is really close to that black dot right there. So of course we're only looking for an approximation, and that's a pretty good approximation. So that means we're in search of an equation for the purple line, which is a tangent line. And again, we're going to call that a linearization as well. So remember, to find a tangent line, we need that point and that slope. So we had to ourselves find the curve and the a value. So the a value is going to be 4. And I need a point, so this is only the x-coordinate of the point. And we chose this x-coordinate 4 because I can easily take the square root of 4, which is 2. So plugging 4 into the square root function, I get out 2. Here's my point. And now to find my slope, I need the derivative of f of x so that I can substitute 4 in. So the derivative of f of x, well, let's remember the square root of x is x to the 1/2. So f prime of x is 1/2 x to the negative 1/2. And I'll go ahead and simplify that a little because I'm going to substitute a number into it. I'm going to rewrite this as 1 over 2 times radical x, so that now when I substitute in my value of 4, I get 1 over 2 times the square root of 4. So that's 1 over 2 times 2. So my slope, my m, is 4. So here's my point, here's my slope. So I'm going to go ahead and substitute in my y minus y1 equals my slope m, so 1/4 x minus x1. So my coordinate point and my slope. So notice we haven't done anything with 4.1 yet. We don't deal with the decimal or sort of that weird value until we have a nice linear function. So we don't want to do anything crazy like plug 4.1 into the square root of x. That was the problem in the first place. Or try to plug it into 1 over 2 radical x. That still creates the same type of problem. We're not going to plug in sort of the ugly number until we get to a line, because it's easy to plug a number into a linear function. So our goal here is going to be to solve for y. So I'm going to take my 4.1 value and substitute it into this x here. So I'm going to have 4.1 minus 4. And then I have this 1/4 in the front, and then I have my y minus 2. So here is me using the linearization. And now I can solve for y. So 4.1 minus 4 is just 0.1, or 1/10. So this is going to be 0.1 and then times 1/4. And then this is still a y minus 2. So now let's sort of think about how we can solve this. So I have this fraction here and this decimal. So let's instead think of, I'm going to go ahead and bring it up here. So I'm going to write this as y equals 1/4 times 1/10. So I've elected to rewrite the decimal as a fraction so that I can have at least all fractions. And then plus 2. So I sort of did two things at once. I added the 2 to the other side, and I rewrote 1/10 as a fraction. So in other words, this is now 1 over 40 plus 2. And at this time, I really want us to think about why this makes sense, at least right now. So if I have the square root of 4.1, well, 4.1 is a little bit bigger than 4. And if the square root of 4 is 2, then the square root of 4.1 has to be a little bit bigger than 2. So this is a little bit bigger than 2 by 1 over 40. So we can go ahead and keep going and leave our answers as fractions, so we can turn 2 into 80 over 40, so that we can think about this as 80 over 40 as 81 over 40. Or if we knew that this 1 over 40 as a decimal is 0.025, then we can maybe even see clearer that this quantity is in fact 2.025, so that definitely sort of makes sense as the square root of 4.1. It's a little bit bigger than 2 because the square root of 4 is 2. So this is, of course, an approximation to the actual value. And leading into what we're going to talk about in a minute, this curve here, this square root of x, is downward facing. That's how I want to describe it right now. It's got a formal term, but right now I want to think about this square root of x function as downward facing. And because of that, the purple tangent line is above the curve. So our approximation, remember, we found this purple point when we did this tangent line approximation. So right now, this purple point is this value, 2.025, right here, which is an over approximation for the actual value. And I say over approximation because I can see that the tangent line is resting on top of the curve because the curve has this downward facing. In other words, if I thought about it like a bowl, this bowl would not be able to hold water. So this curve has this downward angle. So I'm not talking about increasing, decreasing. I'm talking about, try to highlight it a little bit, focus on the curve itself. It curves downward. So I have this downward facing curve and the tangent line must rest above it. So because the tangent line is above it, our tangent line approximation, our linearization, is an over approximation for the actual value. Because let's remember, the actual value is the one on the black curve right there. So I can see the purple dot is above the red dot. So our linearization is an over approximation. And we'll get a little more formal with that in a second. For a second example, we want to use a linearization, or again, a tangent line approximation, to approximate cosine of 1.5. So we definitely right now cannot solve something like this without a calculator. We only know how to substitute values in that exist on the unit circle, and 1.5 is not on the unit circle. But 1.5 is pretty close to pi over 2. So that's the number I should be thinking about, of course pi being about 3.14. And if I divide 3.14 by 2, that's pretty close to 1.5. So with these linearization problems, I need to find the function, and hopefully we can see that the function itself would be cosine x that we're trying to approximate at the value 1.5, but the a value that I need to choose is one that I can easily substitute into the function cosine x and get out a value. So a is not 1.5 here. A is going to have to be pi over 2 because I can easily substitute pi over 2 into the cosine function because this is on the unit circle, pi over 2. So my coordinate point is going to be pi over 2. And if I substitute pi over 2 into cosine, that value is 0. So my coordinate point is pi over 2, 0. And then I need to find my slope. Now to find my slope, I need to find the derivative of cosine, which we know is negative sine x. And then I need that slope to be a number, so I need to plug pi over 2 into sine x, or negative sine x. So if I substitute in pi over 2, I get negative sine of pi over 2, and sine of pi over 2 is 1, and there's that negative in front. So my slope, my m value for my tangent line is going to be negative 1. So my tangent line is going to be y minus 0 in this case. So here's my y1 equals m. My m value was negative 1, and then times x minus pi over 2. Alright, so here's my tangent line approximation. So the cosine function is pretty close to this tangent line at the value pi over 2. So now let's go ahead and sketch what's happening. So the sketch is just helping us support our answer. That line got a little not straight there. So cosine, if we remember the graph, starts at 1 on the y-axis, and then it's going to go ahead and look something like this, where of course this first value here is pi over 2, and then right here I have pi, and then 3 pi over 2, and then of course completing one full period, I get back to 2 pi, which is 0. So what we're doing is we're analyzing what happens, we're drawing our tangent line right here. So our tangent line is now this red line here right at the value pi over 2, 0. And we are using that point to approximate 1.5, which is going to be slightly less than pi over 2, because remember pi is 3.14, so our value of 1.5 is maybe right about here. So we are finding the point on the curve. So let me use a different color here. So at 1.5, we're finding this point, on the tangent line, when we're really interested in finding the exact point on the curve. But of course, we already said that we can't do that without a calculator right now. But we will be able to approximate it using our tangent line. So we're about to find the y value of this blue point right here. So let's go ahead and do that by substituting in our value into x. So our 1.5. So we have y equals, so that's a 0 there. So negative 1 times 1.5 minus pi over 2. Now looking at this isn't quite as easy to simplify as the last one is, especially because in order to do this, to get out a decimal type number that we can recognize as the approximation, I would have to also approximate the value of pi, of course, because it's irrational, and then divide that approximation by 2 in order to get out a number that I can try to identify as the approximation in the context of the graph. So if I wanted a more strict decimal answer, so that it would match what I've done on the graph, I'm going to have to do a little bit more work. I'll tell you right now, this value is 0.070796, and it keeps on going. So that is an approximation to this value right here. But we could stop once we got to this point. This is a numerical answer, right? It's not quite as nice. And of course, I wouldn't want to actually plug this into a calculator like I did to get this answer, because that defeats the purpose. If we had a calculator in the first place, we would have just plugged in 1.5 into the cosine function. So now we have this numerical value. I did plug it into the calculator to get this value out. And let's try to think about why this makes sense. Well, if I plug in pi over 2 into the cosine function, we know that we got out 0. And looking at our graph, I mean, I drew the 1.5 a little bit further to the left because my graph is kind of small. So it looks like this value up here that I've sort of sketched as 0.070796 isn't quite accurate, right? It looks like it's closer to 1 when in fact this is a lot closer to 0. And that's because I moved my 1.5 way over here. So what we're really doing is approximating a number that's a lot closer to pi over 2 right here. So let me go ahead and change colors. Maybe we could see a little bit more. It's like I'm trying to approximate something really, really close to pi over 2 right here using the tangent line approximation. So the value is actually down here, right? So this 1.5, think of it moved over a little bit, and that's where the 0.07 number that's really close to 0 is coming from. But what I really want to focus on now is, again, the idea of whether or not our approximation is an over or an under approximation. And that has to do with the shape of the curve near the tangent line. So the tangent line occurs at pi over 2. What I'm going to do is just redraw this portion near pi over 2. So it would sort of look something like this, right, before it turns and goes up. But right at pi over 2, the curve is downward facing. So again, I want you to kind of think about that. If this was a bowl, this little piece of the bowl would not hold water. So this curve is downward facing. And again, it has a more formal name to it, but that's kind of how I want you to see it right now. Because if I have any downward facing curve at a particular value, if I were to draw a tangent line on that downward facing part, then that tangent line, notice, is resting above the curve. So if I use that tangent line to approximate a value on the curve, that approximation will always be an over approximation, because every point that's on the curve is above the actual curve, because the tangent line is above the curve. So any point is going to be above the actual curve, therefore being an over approximation. So this value, 0.070796, is going to be slightly bigger than the actual value of cosine 1.5. So now let's formalize this idea of over and under approximations. All right, so now let's just focus on this over approximation or under approximation idea. To determine whether our tangent line approximation is an over or under approximation for the actual value on the curve, we need to determine if the tangent line is above or below that part of the curve. So if the curve is upward facing at the point of tangency, so I'm going to draw some examples of what I mean by an upward facing curve. So a parabola would be an example of an upward facing curve, a right side up parabola, or a parabola with a positive leading coefficient would be considered upward facing, because hopefully it's clear to see that if this were a bowl, this bowl would hold water. That's kind of how I want you to think about this upward facing idea. And it doesn't need to be the whole bowl to be considered upward facing. If I just had sort of half the bowl here, that would be considered upward facing, as would the other half of the bowl. And the idea is that if I'm upward facing, any tangent line that I draw at any point of tangency, so if I pick any point on these upward facing curves, the tangent line, sort of missed there, the tangent line that I draw would be below the curve, would always be below the curve. So I don't want you to think to the left or to the right. As you can see, kind of as my tangent line moved over here, that might be an inclination how you want to describe it, but we always think about tangent lines as above or below. So in this upward facing case, the tangent line would be below. So similarly, if I picked one on these sort of half pieces, my tangent line would be below, which is what this next part says. If our tangent line is below the curve, we will have found an under approximation to the actual value on the curve. So if my tangent line is below the curve and I find a point on the tangent line as opposed to on the curve, then that point will have been an under approximation because I'm below the curve. And then if the curve is downward facing, so we're thinking about the exact opposite here. So we have a parabola with a negative leading coefficient, so this bowl that cannot hold water, or half of a bowl in that same type of position. Any tangent line that I were to draw at any point on one of these downward facing curves, we'll notice now these red lines, these red tangent lines, are above the curve. So if I use one of these tangent lines to approximate a value on the black portions, well, that's going to be an over approximation because my curve is downward facing. So again, these are examples of upward facing over here, and these are downward facing over here. So that means we're going to need to know what the graph of our function looks like in order to determine whether or not the curve is upward facing or downward facing. And a little bit later, we'll be able to determine this idea of upward or downward facing, or for those of you who are familiar, concave up and concave down, using some applications of derivatives. But for now, we're going to focus on knowing what the graphs look like.